Geographic Information System, Spatial Measurement. Objectives. In this chapter, we will discuss about the spatial measurements, that is ratio, interval, ordinal, nominal, discrete versus continuous data, accuracy, precision and consistency. Spatial measurement. The type of spatial measurement system used may have a dramatic effect on the interpretation of the resulting value. A distance of 20 kilometers is twice as far as 10 kilometers, and something that weighs 100 pounds is one-third as much of something that weighs 300 pounds. But someone who came in first place in a race may not have done 3 times as well as someone in the third place, and soil with a pH of 3 is not half as acidic as soil with a pH of 6. To carry this even further, someone at 60 years old is twice as old as someone that is 30 years old, but the older of the two individuals can only be twice as old as a younger individual, just once in the lifetime. The significance of this discussion on a number is that all numbers cannot be treated the same. It is important for you to know that the type of measurement system being used in the raster data set so that the appropriate operation and function can be implemented and the results will be predictable. Measurement values can be broken into 4 different types: ratio, interval, ordinal and nominal. Spatial analyst does not distinguish between the 4 different types of measurements when asked to process or manipulate the values. The most mathematical operation works well on ratio values, but when interval or ordinal or nominal values are multiplied, divided or evaluated for the square root, the results are typically meaningless. On the other hand, subtraction, addition and Boolean determination can be meaningful when used on interval and ordinal values. Attribute handling within and between raster data is most effective and efficient when using nominal measurements. The different measurements are ratio, interval, ordinal, nominal, discrete versus continuous data. Ratio. The value from the ratio measurement system are derived relative to a fixed 0 point on a linear scale. Mathematical operation can be used on these values with predictable and meaningful result. Examples of ratio measurement are age, distance, weight and volume. The image is showing the ratio measurement where the line is being divided based on the units, where it is a discontinuous or continuous data can be represented in the line format. Second, interval. Time of a day, calendar, years, the Fahrenheit temperature scale and the pH values are all examples of interval measurements. These are values on a linear calibrated scale, but they are not relative to a true 0 point in time or space. Because there is no true 0 point, relative comparisons can be made between the measurements, but ratio and proportion determinations are not as useful. Following image, the image is showing how the pH scale is being divided. Ordinal. Ordinal values determine position. These measurements show place such as first, second and third, but they do not establish magnitude or relative proportions. How much better, worse, prettier, healthier or stronger something cannot be demonstrated from ordinal numbers. For example, a runner who was in first place in the race probably did not run twice as fast as a second place runner. Knowing the winners only by place, you don't know how much faster the first place runner was compared with the second place runner. Nominal. Values associated with this measurement system are used to identify one instance from another. They may also establish the group, class, number or category with which the object is associated. These values are qualities, not qualities, with no relation to a fixed point or linear scale. Coding schemes for land use, soil types and other attributes qualify as nominal measurements. Other nominal values are social security numbers, zip codes and telephone numbers. Discrete versus continuous data. A second subdivision of the value assigned to each cell are the values representing discrete or continuous data. Discrete data. Discrete data, sometimes called categorical data, most often represent objects. These objects usually belong to a class, for example, soil type, a category, for example, land use type, or a group, for example, a political party group. A categorical object has known and definable boundaries, and integer value is normally associated with each cell in a discrete raster dataset. Most integer raster datasets can have a table that carries additional attribute information. Floating point values can be used to represent discrete data, but this is not common. Discrete data is best represented by ordinal or nominal numbers. Continuous data. A continuous raster dataset or surface can be represented by a raster with floating point values, that is referred to as a floating point raster dataset, or occasionally by integer values. The value of each cell in the dataset is based on the fixed point, such as sea level, a compass direction, or the distance of each location from the phenomena in a specified measurement system. For examples of the continuous surfaces are elevation, aspect, slope, the radiation level from a nuclear plant, the salt concentration from a salt marsh as it moves inland. Floating point raster dataset do not have a table associated with them because most, if not all, cell values are unique, and the nature of continuous data excludes other associated attributes. Continuous data is best represented by ratio and interval values. Many times, meaningless results will occur when combining discrete and continuous data. For instance, adding land use to elevation, which is a discrete data, is added to a continuous data. A value of 104 on the resulting raster data set could have been derived from adding the single family house land use type with a value of 4 to an elevation of 100. Accuracy. Accuracy is the degree of which information on a map or a digital database matches true or accepted values. Accuracy is an issue pertaining to the quality of data and the number of errors contained in the data set or a map. The fundamental issue with respect to data is accuracy. Accuracy is a closeness of results of observation to the true value or values accepted as being true. This implies that observation of most spatial phenomena are usually only considered to estimate of the true value. The difference between observed and true or accepted as being true values indicate the accuracy of the observation. In a GIS database, it is possible to consider horizontal and vertical accuracy with respect to geographic position as well as attribute, conceptual and logical accuracy. The level of accuracy required for particular application vary greatly. Highly accurate data can be very difficult and costly to produce and compile. Quality. Quality can simply be defined as the fitness for use for a specific data set. Data that is appropriate for use with one application may not be fit for use with another. It is fully dependent on the scale, accuracy, the extent of the data set as well as the quality of the other data sets to be used. The recent US Spatial Data Transfer Standard DTTS identifies 5 components to data quality definitions. They are lineage, positional accuracy, attribute accuracy, logical accuracy and completeness. Lineage. The lineage of the data is concerned with historical and compilation aspects of the data such as the source of data, the content of data, data capture specifications, geographic coverage of the data, compilation method of the data, transformation methods applied to the data, the use of an pertinent algorithm during compilation, for example, linear simplification feature generalization. Positional accuracy. The identification of the positional accuracy is important. This includes considering the inherent errors, that is nothing but the source errors and operational errors which are introduced errors. A more detailed review is provided in the errors section. Positional accuracy is expected deviance in the geographic location of an object from its true ground position. This is what we commonly think of when the term accuracy is discussed. There are two components to position accuracy. These are relative and absolute accuracy. Concerns the accuracy of the data elements with respect to the coordinate scheme. For example, UTM. Relative accuracy concerns the position of the map features relative to one another. Often, relative accuracy is of greater concern than absolute accuracy. For example, most GIS users can live with the fact that their survey township coordinates do not coincide exactly with the survey fabric. However, the absence of one or two parcels from a tax map can have immediate and costly consequences. Attribute accuracy. Consideration of the accuracy of attributes also help to define the quality of the data. This quality component concerns the identification of the reliability or the level of purity, that is nothing but the homogeneity in a data set. Attribute accuracy is equally as important as position and accuracy. It also reflects estimates of the truth. Interpreting and depicting boundaries and characteristics for forest strands or soil polygons can be exceedingly difficult and subjective. Most resource specialists will attest to this fact. Accordingly, the degree of homogeneity found within such maps boundaries is not nearly as high in reality as it would appear to be in most maps. Logical consistency. This component is concerned with determining the faithfulness of the data structure for a data set. This typically involves the spatial data inconsistencies such as incorrect lines intersection, duplicate line or boundaries or gap in the lines. These are referred to as spatial or topological errors. Completeness. The final quality component involves a statement about the completeness of the data set. This includes consideration of the horizon, the data unclassified areas and any compilation procedures that may have caused data to be eliminated. Precision or resolution. Precision refers to the level of measurement and exactness of description in the GIS database. Map precision is similar to decimal precision. Precise location data may measure position to the fraction of a unit, that is meters, feet, inches, etc. Precision attribute information may specify the characteristics of a feature in a great detail. As an example of precision, say you try on two pairs of shoes of same size but different color. One pair fits as you would expect, but the other is too short. Do you suspect a quality issue with the shoe, or do you buy the shoes that fit? Would you do the same when selecting the GIS data for a project? No. It is important to realize, however, that precise data, no matter how carefully measured, may be inaccurate. Surveyors may make mistakes or data may be entered into a database incorrectly. The level of precision required for a particular application varies greatly. Engineering projects such as roads and utility construction require very precise information measured into millimeters or tenth of an inch. Demographic analysis of marketing or electoral trends can often make do with less, say to the closest zip code or precinct boundary. Highly precise data can be very difficult and costly to collect. Carefully surveyed location needed by utility companies to record the location of pumps, wires, pipes and transformers cost 5 to 20 per point to collect. Precision refers to the amount of detail that can be discerned. It is also known as granularity or resolution. The latter term is commonly used in GIS and related fields and is adopted here to avoid confusion with the statistical concept of precision as observational variance. All data are limited resolution because no measurement system is infinitely precise. Resolution is also limited because geospatial databases are intentionally generalized. Generalization includes elimination and merger of entities, reduction of detail, smoothing, thinning and aggregation of classes. Generalization is inevitable because at best geospatial database can encompass only a fraction of the attributes and their relationships that exist in the real world. Resolution affects the degree to which a database is suitable for a specific application. The resolution of the database must match the level of detail required in the application. Low resolution do not have the same negative connotation as low accuracy. The low resolution may be desirable in certain situations, such as when one wishes to formulate general models or examine spatial patterns at a regional level. Resolution is also important because it plays an important role in interpreting the accuracy. For example, two databases may have approximately equal spatial accuracy level, but their spatial resolution are significantly different. Then the accuracy level do not denote the same level of quality. One would generally expect accuracy and resolution to be inversely related, such that a higher level of accuracy will be achieved when the specification is less demanding. Spatial resolution. The concept of spatial resolution is well developed in a field of remote sensing, where it is defined on the term of ground dimension of the picture elements or pixels making up a digital image. This defines the minimum size of the objects on the ground that can be discerned. The concept is applicable without modification to the raster database. For vector data, the smallest feature that can be discerned is usually defined in the terms of rules for minimum mapping unit size, which depends on map scale. Spatial resolution is related to but distinct from the concept of spatial sampling rate. Resolution refers to the fineness of detail that can be observed, while the sampling rate defines the ability to resolve patterns over space. For remotely sensed images, resolution refers to the pixel size, that is nothing but ground area resolved, and sampling rate to the space between pixels. Thus, in theory, one could mix high spatial resolution with low sampling rate, that is small pixels with large gaps between them, or low spatial resolution with high sampling rate, large pixels that overlap. Normally, a resolution and sampling rates are approximately equal. Temporal resolution. Temporal resolution refers to the minimum duration of an event that is discernible. It is affected by the interaction between the duration of the recording interval and the rate of change in the event. Events with a lifetime less than the sampling interval are generally not resolvable. At best, they leave a smudge like pedestrians on the 19th century daguerreotypes. This has been referred to as the synopticity problem. A shorter recording interval implies higher temporal resolution, just as fastest film has given us the ability to photograph quickly moving objects. For geospatial data, the situation is more complicated because interaction between the spatial and thematic resolution must also be considered. In general, one cannot resolve any event which during the time interval required for data collection changes location in space by an amount greater than the spatial resolution level. Likewise, one cannot resolve any event for which theme changes to a degree that would be discernible given the thematic resolution level. There is a clear distinction between the resolution and sampling rate in the temporal domain. Sampling rate refers to the frequency of repeat coverage, while resolution refers to the time collection interval for each measurement. For example, motion pictures have a resolution of perhaps 1/1000th of a second in one frame, but a sampling rate of 24 frames per second. Geosynchronous satellites are capable of much higher sampling rates than the sun synchronous satellites, that is, repeated coverage of several times per minute versus several times per month. Resolution, however, is a function of the time required to obtain spectral reflectance data for one pixel. Thematic resolution. In the thematic domain, the meaning of a resolution depends on the measurement scale. For quantitative data, resolution is determined by precision of the measurement device. For categorical data, resolution is defined in terms of the fitness of category definitions. Land cover classification systems used in remote sensing are useful models to illustrate resolution. These systems define the level of detail in taxonomical definition in terms of the spatial resolving power of the remotely sensing system. This illustrates the interdependency between space and the theme when extracting the spatial information, that is, land cover class boundaries from thematic information, that is, spectral reflectance data. Consistency. Consistency refers to the absence of apparent contradictions in a database. For geospatial data, the term is used primarily to specify conformance with certain topological rules. These rules vary with dimensionality. For example, for one point may exist at a given location, lines must intersect at nodes, polygons are bounded by lines, etc. Elimination of the topological inconsistency is usually a prerequisite for a GIS processing, such that the most databases are topologically cleaned before being released. Topological consistency is one aspect of consistency in the spatial domain. The spatial inconsistencies can also be identified through redundancy in the spatial attribute. On the other hand, redundancy may be complete since there is a unique state code for each state. Non-redundancy implies that there is an independence between two attributes such that meaningful consistency constraints do not exist. Little work has been done on consistency in temporal domain, although a framework for temporal topology has been developed. For example, since a given location is only an event can occur at one time, an inconsistency exists if a different entity appears at the same location on two maps of the same date. Since events have a duration, this idea can be extended to identify events that exhibit temporal overlap. In the thematic domain, the ability to identify inconsistencies require the level of redundancy in the thematic attribute. For example, three socio-demographic variables: population, mean household size, and the total number of households. Of course, the identification of an inconsistency does not necessarily imply that it can be corrected or that it is possible to identify which attribute is in error. Note also that the absence of the inconsistency does not imply that the data is accurate. Thus, consistency is appropriately viewed as a measure of internal validity. Despite the potential to exploit redundancy in attributes, tests for thematic consistency are almost never carried out. Summary: the quality of data sources for GIS processing is becoming an ever-increasing concern among GIS application specialists. With the influx of GIS software on commercial market, the accelerating application of GIS technology to problem-solving and decision-making roles, the quality and reliability of GIS products is coming under the closer scrutiny. Much concern have been raised as the relative error that may be inherent in GIS processing methodologies. While research is ongoing and no finite standards have yet been adopted in the commercial GIS marketplace, several practical recommendations have been identified which help to locate possible error sources and define the quality of data. The more accurate and precise the data, the higher the cost to obtain and store it, because it can be very difficult to obtain and will require larger data files. For example, a 1 meter resolution aerial photograph will cost more to collect increased equipment resolution and cost more to store the greater pixel volume than a 30 meter resolution aerial photograph. Highly precise data does not necessarily correlate to highly accurate data, nor does highly accurate data imply high precision data. They are two separate and distinctive measures: relative accuracy and precision, and the inherent error of both precision and accuracy of GIS data determine the data quality.